Welcome to the lesson 4 of industrial instrumentation. In this lesson, I will cover strain gauge, one of the very important sensor in instrumentation. However, before I start this lesson, I must solve, because as I promised that at the end of the lesson 3 that I have given the lesson 3 problem 3.4 to 3.6, which I will solve in this class. Now, problem number 3.4, as you know, is the magnitude of the dynamic error is, or I should write dE, mod of dE should be less than equal to 0.01, because you know that it is a first order instrument. Even though I told that the error can be plus minus 1%, but in the case of first order instruments we have seen that there is no overshoot. So, error should be always less than, can only have it should be less than, that means it should be always 0.99 instead of 1.01. So, if it is there, so the magnitude ratio we know equal to y by k by x. So, it should be 0.99, because 0.01%, 1%. So, it is 0.01 should be less than equal to y by k by x, right. And as you know, this is equal to 1 upon under square root 1 plus omega tau square. Now, omega is given, let us calculate for omega equal to 4. So, if I calculate for omega frequency of 4 hertz, so it will be 2 pi into 4, because f equal to 4 hertz as it is given. So, it will be omega square will be equal to 631. So, it will be 0.981 into 1 plus omega square tau square equal to 1. So, it will give you omega square tau square equal to 0.01936. So, tau will be equal to under the square root 0.01936 divided by omega square is 631. So, it will give you tau equal to 5.6 millisecond. Similarly, if we take f equal to 1 hertz, because we say that the frequency will lie between 1 hertz and 4 hertz. So, we will get tau equal to 0.0226 second. So, I should say that the tau should lie between 5.6 milliseconds and 0.0226 second. That means 5.6 millisecond, tau 0.0226 seconds. If the tau lies between this, the time constant lies between these values, so I can handle the signal for a first order instrument of 4 hertz to 1 hertz to 4 hertz. Now, let us solve the problem number 3.5. 3.5, you see, we have to find the highest frequency, right. That was the problem. It is also a first order instrument. So, problem number 5, solution to problem 3.5. So, it will look like d equal to y by k by x minus 1. It is here the error is plus minus 5%. So, obviously, so it will be 0.95 less than equal to 1 upon root over 1 omega tau square. Sorry, that was a given. So, I can write that from this omega tau square will be less than equal to 0.108. So, I can write omega will be less than equal to 0.01095 radian per second. So, I have not solved the intermediate steps that you can do, but this is our principle how we can find the value, and this is our answer. So, if omega is less than that, I mean that means it can handle the frequency which has a circular frequency value of 0.01095 radians per second. Now, problem number 3.6 rather. So, the solution to problem 3.6, it looks we have a dynamic error of plus minus 6%, right. We have given error constant xi, you have given 0.6, and since it is a first order instrument, so it will lie between sorry, it is a second order instrument. So, it will lie between 0.94, it can overshoot. So, plus minus both plus minus 6% will be valid here. So, y by k by x equal to 1.06, right. So, we have two equation for this, that means 1.06 we know in this case 1.06 greater than equal to 1 upon, if I take 1 minus omega by omega n whole square plus 2 xi omega by omega n whole square half. Oh, I am sorry, I think there will be no square here. So, this will be, so it will get this is one and another one will be 0.94, it is 0.94 greater less than equal to 1 minus omega by omega n whole square plus 2 zeta 2 xi omega by omega n whole square to the power half. So, if we solve these two, so I will get omega n greater than equal to 730 radians per second. This is our answer, right. Now, let me go back to the our today's lecture. It is strain gauge. Now, contents as I told, solution to the problems of 3.4 to 3.6 of lesson 3, application of strain gauge, derivations of gauge factor, composition of the strain gauge material, bonded metal foil gauge, gauge length, backing material, adhesives, semiconductor strain gauge in a Wheatstone bridge, and temperature compensation scheme, and problem on strain gauge. We will solve some problem later on also. Now, you see that strain gauge is basically a device, is a when it is subjected to some force, that means if there is a stress, there will be a change of strain. That means what will happen, that is there is a change of resistance. So, that change of resistance can be calibrated that or measured and can be in future can be calibrated in terms of in terms of either load or displacement. Now, directly this strain gauge is used for the measurement of load, indirectly it is used for measurement of displacement, small displacement, as well as for measurement of pressure. We will see later on that it is used for the measurement of the pressure when it is used in conjunction with the diaphragm gauge, right. Now, let us look at so that is the basic application of strain gauge. Now, let us look at the derivations of the gauge factor of the strain gauge. Now, I mean at the end of the lesson the viewer will know the derivation of the gauge factor of a strain gauge composition and temperature compensation. Let us take a wire of length L and cross sectional area A, and if this wire is stretched or compressed, its resistance will change due to dimensional change, and because of the property of the materials called piezo resistance, which indicates the dependence of resistivity on the strain. Now, resistance R is given by, as you know, this very common equations, rho L by R equal to rho L by A, where rho is the resistivity of the material of the wire, L is the length of the wire, and A is the area of cross section of the wire, right. And if I take differentiation of this, so it will dr equal to A rho dl plus L d rho minus rho L dA upon A square, if all are variable. So, in this case we will get equation like this. Now, see the axial strain we defined as this one, that means axial strain we have defined epsilon A equal to epsilon equal to dl by L. The transverse strain we have defined as epsilon T equal to dd by d, which if you take derivative it will become 1 by 2 or half equal to dA by A, where A is the area of the cross section of the strain gauge. Now, Poisson's ratio is defined by, you see, nu equal to minus epsilon T by epsilon L or epsilon T by epsilon, simple epsilon. Again the volume of the wire V equal to L is V is the volume. So, it is A multiplied by the length of the wire. If we differentiate we will get dV ADL plus LDA. Moreover, we can prove that del V equal to almost equal to A L epsilon 1 minus 2 nu. Now, I will combine these two, so I will get, after combining L and epsilon, we got dl. So, 1 minus 2 nu. So, this can be further simplified. Again we know that del V equal to ADL plus LDA. So, ADL 1 minus 2 nu equal to ADL plus LDA. So, minus 2 nu ADL equal to LDA. Now, dr equal to A rho dl plus L d rho minus rho L into dA upon A square. So, it will be further simplified like this, right, because using the Poisson's ratio. So, we make it positive. So, I will get the equation, the change of resistance equal to dr rho dl, rho is the resistivity of the material of the strain gauge multiplied by dl 1 plus 2 nu, where nu is the Poisson's ratio, divided by A L d rho by A. It can be further simplified if I write like this, dl equal to, because as you know that R equal to, because you know that we know that R equal to rho L by A. So, we have applied this here. So, it will be dr into R, rho dl equal to then R. If we replace rho, then it will be R into A will cancel out. So, we take the L in the denominator and R on the left hand side. So, change of resistance per unit value of the resistance, that we have actually done. So, the gauge factor is given by, it is usually defined as lambda, it is very standard notation for the gauge factor, equal to dr by R upon dl by L equal to 1 plus 2 nu plus d rho by rho upon dl by L. Now, see this this one is actually resistance change due to change of length. This is the resistance change due to change of area. Typically, its value lies between 0 to 0.5 for all materials, and finally, that is the resistance change due to the effect, which is called piezo resistance effect, right. Now, in the case of semiconductor, this will be very high, whereas in the case of metal, I mean this is predominant. In the case of metal, you will find 1, whereas in the case of semiconductor gauge, this is very predominant. You can almost neglect these two parts because it is so high, right. Now, further we simplified, we have introduced d rho by rho upon dl by L equal to pi 1 into E, where pi 1, where E is the modulus of elasticity and pi 1 is the capital pi 1 is the longitudinal piezo resistance coefficients, which can be positive or negative, right. So, with this that gauge factor, expression of gauge factors we have seen. Now, we always want for in the instrumentation systems or for the strain gauge that the gauge factor should be as high as possible, because if the gauge factor are high, then for unit strength I will get more change of resistance, my signal conditioning circuit will be simplified. That is requirement for all sensors, right. Now, let us go to the instrumentation lab and see one practical strain gauge, how it looks like, and which is used as a displacement sensor to make a small I mean displacement sensor. That means, for the small measurement of small displacement, we will come back after some time. It is a displacement sensor based on strain gauges. You have already seen that in all strain gauge measurements, we usually use a bridge, Wheatstone bridge with 4 arms, and for temperature compensation as well as for the larger output, we usually use at least 2 strain gauges, and sometimes you will find the 4 strain gauges. In this displacement sensor, we have 2 strain gauges, and one will be on axial elongation, other will be on axial compression. And if we put these 2 strain gauges on the opposite arm of the bridge, I will get larger output. You see here that there is a strain gauge on this side, you can see here. So, and there is another strain gauge on the back side of this brass plate. And how it works, you see, when I give the displacement like this, you see here the displacements I am giving here. So, this strain gauge will be under axial elongation, and the strain gauge on the back side, that means on this side, will be under compression. So, if I put on the opposite arm of the Wheatstone bridge, obviously I will get double the output, as well as you will find that I will get the temperature compensation in this particular circuit. And this particular displacement sensor is used for the displacement of small displacement like less than 1 centimeter and that type. Welcome back to the classroom. You know, the strain gauge is implemented in several different ways. Number 1 is unbonded metal wire gauge, number 2 is the bonded metal wire gauge, and number 3 is the bonded metal foil gauge, and number 4 is bonded semiconductor gauge, and 5 is diffuse semiconductor gauge. Now, in the case of bonded metal wire gauge, where I can have any unbonded metal wire gauge. Suppose I have 2 pillars, sorry. Suppose I have a 2 pillar, that means 2 pillars here. So, I have put a wire. So, if this pillar is tilted like this one, okay, so some stress will be developed, because this wire will be under tension in that case. So, some stress will be developed. So, it is an unbonded strain gauge, because any wire, a simple wire, if it is under, if you pull on both sides, okay, so it will have certain amount of stress and strain, right. So, this type of also measurement was I mean people used some time back. So, we can call, I mean it is some sort of academic interest, because unbonded wear strain gauge is very uncommon nowadays. Now, next we will find most widely used gauge is bonded metal wear gauge, right. And here in this case that the strain gauge will be bonded on a backing material. It looks like, that means it looks like I have a backing material. So, over which this strain gauge is put like this one, right. So, I have a backing material there. So, we have electrical connections we have taken out. So, these backing materials are various types which will be discussed after some time. So, this is a strain gauge which is called bonded strain gauge. So, it is actually with adhesives, it is to be, this is our backing material, and it is to be placed on a body on which we are interested to measure the stress or strain, right. Third comes the bonded metal wear gauge, which is most widely used metal wear gauge nowadays, because we will concentrate on this a lot, because it has some advantage. We will see that the transverse strain will be very less in this case, because the same technology whatever they are using for making the PCB is also used for making the bonded metal foil gauge. And interestingly, you will find the shape is something like that, this end resistance effect will very much less in the case of bonded metal wire gauge. Now, bonded semiconductor gauge is also there. You will find the semiconductor itself is used to bond on a material. So, it is a, instead of I mean simple wire type of gauge, I am using the semiconductor strain gauge, whereas the diffuse semiconductor is something different. You will find that in the one of the example of the diffuse semiconductor gauge is a pressure gauge, a diaphragm pressure gauge, where the diaphragm material is made of semiconductor. It looks like this. Suppose I have a diaphragm, circular diaphragm, we can see here. So, I have 4 strain gauges here, suppose 2 on the. So, this material is semiconductor, and where I want to make the strain gauges, that portions will be doped. So, if I do dope like that portions, so I will get some gauge there, and this type of strain gauges is called the diffuse semiconductor gauge. It is used for it is a very because of the advantage of semiconductor strain gauge, as I told you earlier, is a high gauge factor, whereas in this almost you can say 60 to 70 times the gauge factor is more than that of the wire type of gauge or gauge made of metal, right. So, composition of strain gauge material, that is very important. You will find that there are many strain gauge available in the markets, and you will find here the different gauge factors we have given. Lambda equal to 2 is a very common type of very cheap low cost strain gauge, is called constant and or advanced. Here the composition is 55% copper and 45% nickel. Then you have isoelastic, which is 36% nickel, 8% chromium, 4% manganese, silicon, and 52% iron. Then you have isoelastic 2. These are all trade name, because you see the strain gauge was first developed. Commercial strain gauges which are developed mostly in the industry. So, they have given some trade names. Later on they gave the composition, but that is the funny name they have given, constant, isoelastic, like that. Then we have molybdenum. Isoelastic 2, which is 36% nickel, 8% chromium, 0.5% molybdenum, and 55.5% iron or steel. So, lambda is 3.6, not very high. Karma, which is lambda equal to 2, because you see what is the use of these two, you will find the applications will be different. If you have that 74% nickel and 20%, because strain gauges are used for various environments. Somewhere you will find the reducing atmosphere, somewhere it is oxidizing atmosphere, somewhere it is very corrosive atmosphere. So, in all these features you will find that in all these different applications you will find you have to use a different type of strain gauges. Then we have armor D, which is 70% iron, 20% chromium, 10% aluminum, lambda is same. Platinum tungsten, rather I should say, it is a very good gauge factor, which is 92% platinum, obviously quite costly, 8% tungsten, and lambda equal to 4, gauge factor is 4. Because if the gauge is higher, gauge factor is higher, obviously I will get the better and better output, because as you know that lambda means dr by r by dl by L. So, whenever the lambda is high, so I will get more change of resistance, right. For the same amount of strain, I will get more change of resistance. So, that is very much necessary, okay, to have a simplify our signal conditioning circuit. Then we have a nichrome V 80% nickel 20% chromium, lambda equal to 2.1, semiconductor strain gauges lambda equal to 130, right. This should be equal, I do not know why it did not come. So, lambda equal to 130, exceptionally high, you will see that compared to all this is almost 60 to 70 times more, at least 60 times more, 60 to 60, I mean 5 times more than the conventional wire. Or please do note one thing, that whether it is a wire type of gauge or a I mean bonded wire gauge or bonded metal foil gauge, the value of lambda does not change. It is a physical property, it depends on the compositions of the materials. People for the over the years they have tested this, they have seen they made some funny composition to get the value of lambda higher and higher. Whether you are using in a bonded metal unbonded gauge, bonded gauge or bonded metal foil gauge, it does not matter, because ultimately the value of lambda depends on the composition of the material which is used to make the strain gauge. So, bonded metal foil gauge, as I told you earlier, it is the most widely used transducer for stress analysis. It consists of a metallic foil pattern similar to the process used to produce printed circuit board. So, as you know the printed circuit board, because it is printed circuit board, what happened that as you know that it is a bakelite type of materials taken and it is covered with copper, then a mask is put on this one, and it is a ultraviolet light falls on that, and whenever there is falls, whenever it is obstacle, so that portions when it put later on in the liquid, some special liquid, you will find that will go out. The same principle is also used for making the strain gauges. The reason I will tell you after some time. So, photo etched metal foil pattern is installed on a backing material. You see here it is a typical metal foil gauge, where in the case of wire gauge these two thickness will be same, whereas you see here all the end resistance are end portions of the strain gauges are made very thick. The reason is, you see when I am subjected to some stress, so I am supposed to that, suppose in this case, suppose I am giving it some tension here. So, all this supposed to have a axial tension, is not it, whereas what will happen, you see here on these portions, this will have a transverse, right. But while I am making the calculations, I have not included this part. So, what I have to do? I have to do in such a way, if I make it thick, so the contributions, so the value of R in these portions will be very, very small, is not it, compared to this portion. So, the contribution to the transverse strain or the transverse strain error in this case will be very, very low. That is the reason metal foil gauge purpose, because in the case of wire gauge I cannot change the dimension of the wire in between, but in the case of metal foil gauge we can do it, because it is the principles of the principle of the printed circuit board is utilized to make this type of gauges. So, these end portions are very thick. So, the resistance small, R small, here R small. So, the error, transverse error will be minimum, transverse strain error will be minimum. You may immediately say, sir, what is the harm if I take a simple stretch of wire like this one? This is not possible. You see that I have to make a sufficient length of the wire, so that the value of R is sufficient. If the R is large, delta R also will be large, please note. So, that will ease our simplified our measurement. If the R is small, R will be small if I take suppose a small length of wire. If I take a full length of wire, this one, so my delta R also will be small, R will be large, delta R also will be large. So, that is in all the funny shape, I mean this type of shape you have to make in the case of strain gauges. This is very simplified, actually you will find there are various parallel, it looks like I have several, you will find that there are several, it means, so that the value R should be that means substantial. So, this value should be very substantial, so that the delta R also will be large, right. So, that is very much necessary. So, is a bonded metal strain gauge, you see this here, this is the backing materials on which we have put, right. Now, gauge length, the proper choice of the gauge length is important factor for some specific applications. Strain is to be measured at the location where stress is maximum, and the strain gauge averages this measured strain over the gauge length, and the measurement can be erroneous due to improper choice of the gauge length, right. So, gauge length is very important. Backing material, it electrically isolates the metallic gauge from the test specimen, right, because you see the in all the cases you will find strain gauge we will put on a Wheatstone bridge. So, it is electrical circuit. So, that electrical, suppose I am interested to measure the strain or a load on a beam, a steel beam. So, in that type of situation, so I cannot connect directly on the steel beam itself. I have to insulate, because we are interested only on the strain. I do not want to make electrical connections with the on the steel beam itself, right. So, that is so it will isolates. First of all, it property is electrical isolates the metallic gauge from the test specimen. Then it transmits the applied strain to the sensor. It provides the surface that is used for bonding the gauge with the specimen surface where the strain is to be measured. The backing material should have a wide temperature range. Polyimide and the glass reinforced phenolic are two commonly used backing material. These are the most commonly used backing material. You see, these are polyimide. So, these are polyimide and glass reinforced phenolic and two commonly used backing material. Now, adhesives, because you know that this bonded metal gauge, I mean wire gauge or foil gauge does not matter, it cannot, I mean you have to use some adhesives. So, usually you have to put some adhesives on which, and there is at least there should be some time of 124 hours you have to keep for the curing or drying up process, right. So, there should be some features, as you know, in the case that while you are installing on a, suppose a pipe, okay. Suppose I have a pipe like this one, so I put on a strain gauge over this one. So, I will put a strain gauge, I want to interested, suppose there is a bending of pipe, how much strain will be developed in that pipe. So, in that case, so I have to put the strain gauge, and I have to, whatever the strain developed on this pipe, okay, after the once it is under tension or compression, same should be transmitted to the gauge itself, right. So, there should be a very strong bonding of the, first of all, the gauge with the backing material, then backing material with the this test specimen, right. If there is some gap, that means between the test specimens and the gauge, so the actual load which is I have given to this this pipe or test specimen cannot be, will not be fully transmitted to the gauge. So, there will be some error which I do not want, right. So, the bond created by the adhesive serves as a mechanical and thermal coupling of the strain gauges and the test specimen. This is very important, because you know the all the strain gauges, since it is a resistance, it is temperature sensitive. So, I have to make all sorts of temperature compensation, and whatever the temperature compensation is there. So, I should have to incorporate that, because you see that if the I am not interested resistance change due to the change of temperature, I am interested into the resistance change due to the change of the strain there, because if it is there is a resistance change due to the temperature, that will be erroneous reading, because I am measuring in the test specimen how much stress is developed, how much load is developed there. So, in that case, if there is some strain developed due to the change of resistance, so that will give us erroneous reading. Adhesives should be accurately transmit the strain given to the test specimen. It should have a thermal, conductance and the expansion characteristics, same as the metal itself or test specimen. Thus, adhesives should not shrink or expand during curing process, otherwise the pseudo strain will be developed in the gauge. This is also very important, because while the curing process means you have to leave for at least 24 hours to dry up or curing process. Once you put the, suppose in a my pipes, I put a strain gauge here, so I put an adhesive, so I have to leave it for 24 hours before drying. Now, during drying up, so during curing process or dry up process, there should not be any pseudo strain developed. If it is developed, then what will happen? You know that that resistance strain gauge will be under tension, so it will give you some false reading. Even though you can compensate for that, you can use some other resistance to balance the bead and all those things, but that is not very desirable, right. Now, epoxies and cellulose nitrate cement and ceramic based cements are some of the adhesives used for making the adhesives, for adhesives. Now, semiconductor strain gauge is most widely used, as I told you, because of its high gauge factor. The only problem with the semiconductor strain gauge is that it is very sensitive to temperature. That means, it is temperature coefficient is very high, so that immediately it changes the value of the temperature, resistance changes as the temperature changes, and also its performance deteriorates in presence of the moisture. That is the main problem in the case of semiconductor strain gauge. Silicon is the basic material for making the semiconductor strain gauge. Usually, silicon is doped with a boron to make p-type strain gauge. It will be n-type strain gauge if it is doped with arsenic, and the resistance of p-type gauges increases with the applied tensile strain, and that of the n-type gauges decreases, right. Now, only problem with the strain gauge, you see that we will see later on, I have to use some dummy gauges for temperature compensation. We will see later on this thing. Now, getting two strain gauges, two semiconductor strain gauges of exactly same value of lambda is very difficult, because in the case of metal gauges, the value of the lambda depends on the composition. If the composition is correct, it does not matter whether you make it wire or metal foil. So, you will get always the same value of lambda, whereas in the case of the slight doping changes, in the case of semiconductor strain gauges, its value of lambda changes. And so, the exactly two gauges having the same value of lambda is very difficult to get. Like beta transistors, two betas, always we say that there is some, it lies between some value, two values. I cannot have a two transistor exactly same beta. I can measure it and make it. Suppose in the complementary symmetry amplifier and push pull amplifier, always we try to make beta of the two transistors same. We pick up and measure, if two are equal, we say these are pair. Now, resistivity of a semiconductor material is given by rho equal to 1 upon q in mu, where I am sorry, this will be where. So, this will be where q equal to charge of electrons, number of charge carriers that depends on the doping, and mu is the mobility of the charge carriers, right. The impurity concentration is typically lies between two values, which will come at the end. The resistivity of the p-type silicon with the concentration, let it comes first, then we will. You see here, the impurity concentration is typically lies between 10 to the power 16 to 10 to the power 20 atoms. The resistivity of the p-type silicon with concentration of 10 to the power 20 atoms per centimeter cube is 500 micromole meter, that is much higher than that of the copper. The strain gauge material shows a change. Now, interestingly, you will see that if you increase this beyond 10 to the power 20, you won't get any much change of the resistivity in the case of if you apply some strain there, whereas if it lies between these two values, you will get sufficient change of resistance in the case of semiconductor strain gauge. That actually we want. The strain gauge material shows a change in resistivity with strain, and this change of resistivity is called the piezoresistive effect, and the mobility of the charge carriers changes due to applied strain, thus causing the large change in resistivity. This is the most important. You see in the case of semiconductor strain gauge, this change of resistivity is very high. That is the reason I am getting the large value. If you remember our main expressions, so our expression was lambda equal to dr by r excuse me dl by l equal to 1 plus 2 nu plus d rho by rho dl by L. So, this term for the semiconductor strain gauges will vary because of this factor. This term is not predominant in the case of metal wire gauges, right. So, that is why I am saying the mobility of the charge carriers changes due to the applied strain, because the mobility depends on the mobility we have seen, right. So, thus causing the large change in resistivity. The advantage, you see the high gauge factor useful for measurement of micro strain, very small strain I can measure, which is not possible with the case of wire type of gauges, whether foil type or it does not matter, foil or wire type. In the case of metal gauge, it is not possible. Small gauge length, so very small strain gauge sensor we can make. So, the dimension of the gauge I can make very small, as I told you earlier, that you see that in the case of pressure sensors, we have seen that small size I can make, which is not possible in the case of wire type of gauges. Now, disadvantage is high temperature sensitivity. Temperature sensitivity we can compensate. It is very easy to say that we can compensate by using the dummy gauges or using 4 strain gauge, but having 4 semiconductor strain gauge having the exact value of lambda is very difficult. Nonlinearity. So, nonlinearity is another factor in this case of semiconductor gauge. Mounting difficulty is also there, because semiconductor is very, I mean, if it is diffused, that is advantage, but if it is not diffused, bonded semiconductor strain gauge, mounting difficulties will be there. And performance deteriorates in the presence of the moisture. And instrumentation, not necessarily you will measure, I mean, without moisture. I mean, sometimes you will have to measure in some moist where superheated steam is there. Sometimes you have to use the corrosive liquids, sometimes we are having a gas which is very hostile in nature. So, in that type of situation, semiconductor strain gauge is not very suitable. Now, see that I will make a temperature compensation, strain gauge temperature compensation is there. So, it is necessary, I will do the temperature compensation, it looks like this. I have an active gauge, one dummy gauge and fixed resistors. You see here, I have an active gauge. You see that in the case of strain gauge, I can measure with a single strain gauge also. Whatever the change of resistance, I will put on a Wheatstone bridge. Suppose there is all the gauges resistance, simple resistance, I put one active gauge. In that situation, there is no problem. I can measure the change of resistance values when it is subjected to strain, but the problem is that you see it won't, there will not be any temperature compensation. That means, due to temperature change, some change of resistance will come. So, my circuit will not take care of that. Whereas, in the case of dummy gauge the meaning is that this gauge will not subjected to stress or strain. That means, suppose I am interested to measure measure the stress developed on this pipe. So, I will put the actual gauge or active gauge on this one, and dummy gauge I will not put over this one. It is also a strain gauge. These are not strain gauge, these two are fixed resistor, simple carbon or any other type of resistor, but these are basically the strain gauge, these two are strain gauge, whereas this gauge will be subjected to strain and this will not be, this will not be subjected to strain. So, whereas this is subjected to strain, this will not be subjected to strain. So, what will happen to this? This will be very close to the pipe, but it is not subjected to any strain. So, whatever the reason is why I am saying that this should be very close to the pipe, whatever the active gauge have the temperature, this dummy gauge should have the same temperature, that I want to mean. If I can do that, so there is no problem. So, always we will measure this this change of resistance by Wheatstone bridge. Now, there are two types of measurement. One case I will use a balanced bridge In other case, we will use the unbalanced bridge. Now, we will first consider the unbalanced bridge. Let us look at. So, in the unbalanced bridge, you will find that, sorry, it is a balanced bridge. So, I have 4 So, this is my output voltage, this is resistance. Let us take a Wheatstone bridge. So, otherwise I cannot write. Suppose this is I2, all current different, R2, this is I4, this is R4, this is R3, current is going in this direction, I3, and this is my excitation Ex, right, and I gave some nodal point A, B, this is A, this is a B, this is C, and this is D. Now, let us analyze this circuit. Okay. For the bridge is to be balanced, points B and D must be at the same potential, So, I can write I1 R1 is not it equal to I4 R4, then I2 R2 equal to I3 R3. So, simply I can divide, if I these two equations, I will get I1 by R1, I2 by R2 equal to I4 by R4, I3 into R3. Now, if there is no current, in the detector, so I1 equal to I2 and I3 equal to I4. So, R1 by R2 equal to R4 by R3, right? Sorry. Right. Now, what will happen? Suppose R1 is the unknown resistance, or our, that means our circuit looks like this. If I redraw the circuit, so R1, R2, R3, R4. So, this is our output voltage. So, suppose now R1 equal to Rx. So, Rx unknown resistance or strain gauge, I can write R4 by R3 into R2, is not it? Now, you see, I can use either R4 or R2 to make the temperature compensation, is not it? I can choose either of this one, because in that case whatever the changes occur in the Rx due to the temperature, the same change will occur also in the R4 and R2. Then either R4 can be dummy gauge, this can be dummy gauge, or R2 can be dummy gauge. Okay. In that case, any of the resistance, if you check R4 suppose for balancing the for as a dummy gauge. So, in that case R2 can be used to balance the bridge. So, this is the case when there is a no current flowing through the detector. That means, I am assuming in that case, that is I will vary R2. That means, if I take a new page, that means so this is R1, R2, R3, R4. So, this is our strain gauge suppose Rx. So, as I told you before, Rx equal to R4 by R3 into R2. So, this is our active gauge, this is our dummy gauge, right. This is used to for making the temperature compensation. So, ambient temperature compensation, because if the ambient temperature changes, this gauge will take care. So, it sometimes is called ambient temperature compensation also, ambient temperature compensation. And R2 and R3 should be of similar type. So, these are fixed resistors, or it can be variable resistors, because this variable resistors to balance the bridge, because suppose I have subjected strain, again I will make EO equal to 0. So, this R2 can be calibrated in terms of the load, right, or displacement, whatever you like, because it can be used for making the displacement sensor also. So, in that case R2 will be calibrated in terms of the displacements, or R2 can be calibrated in terms of the load also. So, it will be dialed, so that you will see, look at, and you will find how much is the load, whereas this will be our temperature compensation, right. We will find that in latter that we will use 4 gauges simultaneously, all are active gauges, to increase the value of the unbalanced voltage, because sometimes I need large unbalanced voltage. So, I can do it. Now, let us go to the problem 4.1. A steel bar of rectangular cross section 2 centimeter into 1 centimeter subjected to tensile force of 20 kilonewton. A strain gauge is placed on the steel bar as shown in the following figure. Find the change of resistance of the strain gauge if it has the gauge factor of 2 and the resistance of 120 ohm in absence of the axial load. The Young's modulus of elasticity of the steel is equal to 2 into 10 to the power 8 kilonewton per meter square, right. It is no question of bridge or anything, simple problem we have given. We have shown this, that it is a, you see here that the installation it is subjected to tensile, is not it. So, it is tensile load here. So, it will be axial. So, there is no question of any transverse. So, there will be axial load, and you have to find that the change of resistance in this strain gauge. It's a very simple problem, right. So, no question of bridge or anything, we have to, with that we will do later on, right. Now, let us solve this problem. Okay, let us take, I am sorry, I can take this one. Here you see lambda is equal to 2, is not it, and E equal to 2 into 10 to the power 8 kilonewton per meter square, P equal to 20 kilonewton, and R equal to 120 ohm. Area of cross sections we have given A equal to 0.02 into 10 to the power 01 meter square. So, stress on the bar is sigma A equal to P by A equal to 20 upon 0.02 into 0.01. So, this will give you 10 to the power 5 kilonewton per meter square. So, epsilon A or epsilon equal to sigma by E or sigma A by E. E is the Young's modulus, 10 to the power 5 by 2 into 10 to the power 8. So, it will be 5 into 10 to the power minus 4. So, dr by r we know by dl by L equal to lambda, is not it? Or I can write dr by r equal to lambda into epsilon A axial. So, delta r or dr will be equal to r epsilon into lambda. So, it is 120 into 5 into 10 to the power minus 4 into what it is the resistance, 5 10 to the power 4 is the strain, multiplied the gauge factor which is advanced probably, yes, this is advanced strain gauge obviously 2. So, this will give you change of resistance 0.12 ohm, right. So, the answer is 0.12 ohm. I have solved this problem to know that you see that how small this change of resistance. It is not very easy task to measure this, and as I told you that just using a one simple you can use one resistance, that means R2, and calibrate R2 in terms of stress or strain is very difficult, and as you look at this change of resistance very small. So, mostly we will see that we will use that unbalanced voltage and we will calibrate that unbalanced voltage in terms of displacements or force or pressure or load, whatever it, and we will use, instead of one gauge we will use 4 gauge, try to gauge 4 gauge. In that case there will be more unbalanced voltage. Okay. Then we have seen that in the case of our displacement center, one gauge will be under compression, another gauge will be elongation. I will get the temperature compensation as well as my bridge unbalanced voltage will also be very high. So, that this will help us to make the circuit, signal conditioning circuit simpler, because if the smaller higher the voltage, the more less will be the error in the measurement also. So, those things is to be considered. So, strain gauges we have covered, we will see later on in the future lesson that it will be extensively used for the measurement of load, right. So, this is the basic sensors which is used, but strain gauge alone cannot be used, it is either in some pressure gauge or some load cell and all those things. And this ends the lesson 4.